Hello everybody and welcome to the NPTEL online certification course on microelectronics, devices and circuits. In our previous lecture we have understood the basic functionality of a transistor and why is it basically working as it should be. We have also understood the various numerical formulas used for finding out the current flowing through the circuitry. We have also gathered a position, or we have also understood or appreciated the role of minority current carriers in the NPN or a PNP junction. We have also seen that it can work in 4 different modes of operation for the purpose of switching as well as for amplification purposes. In this lecture we will be looking into its operation. So, the name of this lecture or the title of this lecture is Operation in Active Mode, Circuit Symbols and Conventions. So, that is the lecture topic, and what we will be looking into in this module or in this lecture is basically NPN in forward active mode. So, once we have understood the NPN in forward active mode, we will be easily able to understand PNP in forward active mode, right. Forward active, if you remember, is when your emitter base junction is forward biased and your collector base junction is basically your reversed biased, right. So, this is your forward active mode junction which you see. We will also look into the 3 configurations of working of this transistor, which is basically common emitter, common base and common collector, and then we will see some of the conventions and circuit symbols used, and then we will recapitulate what we have learned across this module. Now, if you remember in the previous discussion on the previous understanding, we had encountered 2 important terms. One was basically known as alpha and another was basically known as beta, right, and both were, if you look very carefully, both were actually current gains, right, current gain, right. Alpha was defined as IC by IE. So, this is basically your common base, right, current gain, and if you look very carefully, the numerical value will be very close to 1, right, and the reason being that IC is approximately equals to IE, because IB is very small, assuming that we already have this Kirchhoff's this is already there. I would say this to be as very close to 1, right, alpha to be very close to 1. Typically beta is known as common emitter current gain and is referred to as alpha upon alpha minus 1, right. So, this is what we get as a beta here, right. So, it is basically alpha multiplied by 1 minus alpha, right. So, if you take alpha is to be equal to 0.9, right, approximately, then I get 0.9 by 1 minus 0.9. So, 0.9 by 0.1 I get approximately equals to 9, right. Is this clear conceptually? So, I get 9. So, this is beta which you see in a common emitter current gain. So, you see we will discuss this as we move along, but primarily you see that we have tried to find out in our previous discussion the current gain because of a BJT. Now, let me show to you the transistor action, how we can achieve a high gain or a high amplification in this case. That will be the main focus of our topic in this case. So, let me explain to you how this first topic, which is basically NPN transistor in forward active mode configuration or bias. As I discussed with you in the previous turn, in active mode of operation, right, base emitter junction is always forward biased, right, and the base collector junction is always reversed biased. You have to ensure this base collector junction should be forward biased. Now, one important point which you should note down as far as designing of BJT is concerned, if you remember the previous talk, that the IS value, the saturation current value, was depending upon the cross sectional area of the emitter. So, if you have got 2 transistors, both NPN or both PNP, of exactly the same doping concentration, but one having a larger emitter area as compared to the first case, then the second will have a larger current also as compared to the first case. So, this was one of the techniques by which people used to increase the level of current in a structural, by structurally reconfiguring our NPN or a PNP transistor, right. Similarly, you should also be careful. The first point which is to be noted is that your base emitter junction should be forward biased, which primarily means that your emitter base junction of an NPN silicon transistor should be at least, the forward bias should be at least more than 0.7 volts, right, for a silicon, and the reverse bias should be much larger than the forward bias. Please understand this point also. So, you have to be very cautious about two things, that is VBE, base to emitter junction should be at least greater than 0.7. So, the requirement therefore is that VBE should be much greater than 0.7 volts, right, greater than equal to, and VCB, collector to base, should be much larger than VBE, right. So, the reverse bias is typically very large as compared to the forward bias itself, right, and that you should be carefully looking into that properly. So, let us look at the second point. Therefore, the electrons from the emitter are injected across the base emitter junction into the base, and therefore thereby creating an excess minority carrier concentration in the base. We have already discussed this point earlier, and we also saw that the minority carrier concentration will be falling linearly between the emitter base and the collector base junction. As you can see, therefore, the electron concentration at the edge of that junction is approximately, which junction? Collector base junction, is approximately equals to 0. We have also seen this to be true, right. Now, to ensure that the minimum number of electrons get recombined in the base region, right, the width of the base region should be very small as compared to the total length of the dimension of the device. I will explain to you what does it mean, and I will explain this term in a much more detailed manner. It says that the width of the neutral base region, why? Because you see you had initially p type for an NPN transistor, initial p type. Now, you have minority carrier concentration N inserting into it, trying to make it neutral. The base width W, right, this width of the neutral base region must be very small as compared to this minority carrier diffusion length. What is the minority carrier diffusion length? Well, we define diffusion length as the distance at which because of recombination the value of the minority current or the charge carriers falls to 1 by Eth of its maximum value, right. So, if you entered at this stage and you went to a distance of 1 centimeter and you saw that there was a drop in the number of charge carriers by virtue of recombination, and we saw that 1 Eth of the charge has actually 1 Eth. So, 1 by E of the charge has actually fallen down, then we define that length to be a diffusion length. So, if your width, base width is even smaller than that, then by the time the electron starts moving, I would expect to see that no large diffusion has taken place, or no large recombination has taken place, sorry. So, what we will expect to see therefore is that try to keep the width of the base much smaller than the active diffusion length of the minority current carriers, right, and that is what this will minimize your recombination effect. Then the obvious question asked is, then why should we have the recombination in the first place? Well, the reason for that is then we have a control, we have a current control device here. By controlling the base current, I can control the collector current, right, because I equals to IB plus IC, and therefore, if I want to reduce my IC, I need to increase my IB large, make it large, and as a result effectively VBE controls the value of IC by making the IB value vary from point to point or from value to value, right, and that is what one should be looking into in a detailed manner. Let us look at therefore the NPN transistor in the forward active mode configuration, and we define this and we generally therefore put a arrowhead here and a arrowhead here, assuming means implying that these are variable power sources or variable power supplies which is there with you. This RE and RC, right, are the basically the resistances. This takes care of the Schottky resistance at the contact, because the contact with this side and this side will have metal contact, right. We had discussed this point earlier also. This will be metal, this will be metal also. So, both are metal. So, metal contact will have some resistances, plus the wire will have some resistances, plus any resistance which you want to put it in the external world in order to restrict the current or get a voltage output, you put those resistors. So, add up all those things and we get a collector resistance here, right, collector resistance here, and we also get a emitter resistance here, right. Now what will happen is, once this current flows here and IC multiplied by RC, that is the voltage drop across this RC, right, that is the output voltage VO, right, and you will be giving a small voltage here, input voltage is VBE. So, output voltage by del VBE, del V0 will be your gain for a transistor, right. So, this is a very simple basic form of a transistor as an amplifier. As long as you are able to sustain a large current across the collector end, that multiplied by the collector resistance will give you a large voltage drop. This voltage drop will therefore change depending on the value of VBE. So, VBE is therefore your input voltage, and therefore output voltage by input voltage will give you the current. If you can see very clearly, your base emitter junction, this pink side is basically my depletion, this one is the depletion width, is very small because it is forward biased, and this is relatively large in dimension because it is reversed biased, right. And therefore, base collector junction will have larger width and therefore larger effective bias, whereas emitter base junction will have a relatively a lower depletion width, and therefore a large current will be flowing between the base and emitter junction. Now at this stage, what we have not done or what we have understood therefore is two important point I should take care here before we move forward is, one is what is known as a base width modulation effect. So, this is known as, I will explain to you what is known as a base width, right, modulation effect, again a second order effect in a BJT. If we have a base which is something like this, right, then if you look very carefully, if it is a forward active mode, and assuming this to be as NPN, and this is emitter base collector, then we bias it such that this emitter base junction to be forward biased, and this base collector junction to be as reverse biased, right. This is reverse biased. So, I define, let me suppose BC and VBE. Now, you see, because of VBE there will be a thin depletion region here, but since it is a forward bias it will be very thin in nature dimensions, whereas because of VBC I will expect to see a larger depletion width here, fine, is it okay, fine. So, I will see a larger, so if this is say x1, right, and this is x2, then obviously x2 will be larger than x1, because this is reverse biasing, because your base collector is reverse biased and your emitter base is basically forward biased, fine. With this knowledge, let us do one thing, let us fix up VBE, right, and increase the value of VBC. You go on increasing the value of VBC. As you go on increasing the value of VBC, what will happen, that this depletion width will go on increasing, because you know very well that in a PN junction diode or in a simple PN junction, if you increase the reverse bias, the depletion width becomes larger and larger. So, what will happen is the depletion width will become larger and larger, right. So, x2 will become still further more and more, right. When x2 becomes more and more, you could easily appreciate that the effective base width reduces, effective base width reduces, fine. As it reduces, now you allow a larger amount of current to flow through it, because now the number of minority current carriers there or the number of holes there is still smaller. Is this concept clear? Therefore, I will explain once again what I was trying to say, because this concept will be important to understand why the collector current is not behaving as an ideal current source. What will happen therefore is that as you increase the value of VBC, base to collector voltages, since it is a reverse bias base to collector voltage, as you make the base to collector voltage go high and higher, the depletion width on the base to collector region, the depletion width will also increase. As a result, what will happen is that the depletion width on the base to collector junction will eat away into the active area of the base. So, your base was something like this, your base was something like this. Now, initially your collector base junction was reversed bias like this. Now, increase the bias and this has shifted, this line has shifted to this part and it has become something like this and it has become something like this. So, which means that this much amount of base is gone therefore, and the effective base width is reduced to this much amount only, right. As a result, the EHP electron hole pair recombination will also be reduced, right, and more of IE will be allowed to go to IC, and therefore, your alpha value will increase, and as a result the current will not remain constant, but current will change with respect to VCB. Please understand this point very carefully. Till now we were all explaining that as VCB becomes larger and larger, or as VCB is increasing, as long as it is reverse bias, collector base junction is reversed bias, independent of its value the current will always remain constant, and what we were therefore doing was that we were actually assuming therefore it is behaving like a constant current source, the collector is behaving as a constant current source, and if you remember the last talks last part, you will see that we had removed the collector and replace it by a constant current source, right, and IC was equals to alpha times IE, and we have shown that this is the constant current source. But in reality you will see that depending on the value of VCB it will start, the IC will change. So, higher the value of VCB, I would expect to see a higher change, not because of a large electric field, but because of a reduction in the effective base width, which effectively means that the recombination of electron hole pairs will be minimized, and therefore more of emitter current will reach toward the collector side, and at the collector side they will register a current, right, and that is what is known as the is also known as base width modulation effect, right. So, we do a small change in our understanding and say that no, in second order effect, if base width is very small and we are varying our VCB to a larger extent, we would expect to see a large change in the base width, effective base width, which will result in a large change in the output current, right. So, this is what we learn and we have understood as far as this course is concerned. One more thing which I wanted to point out and maybe interesting, maybe of interest to most of you, is that if you remember that if I have a P and N, right, and if my doping concentration is low, then the depletion width is larger on that side. So, just keep this in mind that if the doping is low, right, and you apply a bias in a PN junction, then the depletion width will be larger in that semiconductor in which the doping is low, fine. So, please be careful that the lower the doping, more will be the depletion width. So, you see this also adds to the effective base width modulation effect. Why? Because intrinsically we had discussed the point that the base will have a much lower doping, right. So, it is very low doped. When it is very low doped, you automatically end up a larger depletion width on the base side, right. So, the variation on the base side will be much larger as compared to the collector side, and as a result your emitter base junction, so or the effective base width will be further minimized in the case of this one, right. As a result you will have increase in current. So, if you plot collector current versus VCB, right, ideally I should get something like this, but if you see it will be something like this. So, this is ideal current source, whereas this is a non ideal current source, right. Therefore, this will have Z out equals to infinity, but this will have a finite Z out. Z out is the impedance, output impedance. So, current source, ideal current source will have a infinite output impedance, whereas a non-ideal current source will have a relatively lower influence current source. So, coming back to therefore the basic issue, once again we saw that for a active mode, base emitter is forward and the base collector is reverse bias. We again came back to the same position that if you have an NPN, this is basically the thicker arrow is basically my majority. So, majority current carriers are inserted very fast and you get a large amount of electrons coming here. This is what is known as the recombination. So, IB2 is basically because of recombination between electron hole. So, this is basically my recombination current, right, which is because of electron hole pair getting recombined, and therefore, the current which is flowing is basically IB2 because of that. And please also understand that since this is forward biased, holes can easily punch through this emitter base junction with this one and will result in some current IB1. So, there are two phases of current, IB1 and IB2. IB1 is primarily because of holes and IB2 is primarily because of recombination of electron hole pairs in the base region. We understood this point earlier also, and we have also got the principle correct. Let us see how we can look into we have looked at NPN. Can we look into a PNP as well, which is basically a NPN and PNP in active forward active mode. The same concept as in the previous case, only thing is the polarity of the battery will now be changed or reversed, and you will have VBB in which the positive end is connected to P type and VCC negative end is connected to P type. So, this will be reverse biased and this will be forward biased. So, we are keeping the same concept exactly the same as in the previous case and trying to formulate a policy for finding out the current. Here also IE will be equals to IC plus IB, right, and this will be the only thing is because whole current is basically the conventional current, therefore, we see that the direction of the arrowhead actually shows me the direction of the holes, flow of the holes, right. So, this arrowhead which you see here, this one is basically the direction of the holes, right, and therefore, this shows the holes will be moving in this direction. As a result, the holes, so electrons will combine here, electrons and holes will be combined to recoup that many number of electrons. Electrons will be moving in this direction. So, holes will be coming out in this direction. So, you see IB2 to be that electron, right, and the rest of the electrons holes move in this direction, and therefore, IC is always in the outward direction. So, IE equals to IB plus IC, RC, RB are the resistances which you see in a typical operation. Common emitter configuration of the BJT, because we will now enter into. So, now we will be seeing maybe next two lectures or one lecture is that given therefore a transistor, can we find out the current flowing through any of the nodes of the transistor, provided we know the bias given to that particular node, right. So, what we do, we give a particular set of bias to the transistor, any bias by giving forward or negative bias. That means, can we therefore take a transistor, fit into all the 4 modes available to us and check out how the currents will flow with respect to the variation in the biases in those transistors. So, that we will learn in the next 3 to 4 slides in our understanding of this this basic concept here. We will deal also one by one as we move along. We will deal one by one in a detailed manner, and we will see how it works as an inverter and all those things. Before we move forward, therefore, let me give you a very simple brief understanding of a BJT as a inverter. That means, if I have got a BJT here, a bipolar transistor, and I apply a bias here, and this is my VCC and this is my ground, right, this is RC here, and I take the output from here, V out, and V out to ground I take the output. So, this is positive, negative, and this is my input I give here, right, and this is my base, and this is basically, if you look at the arrowhead, since arrow is pointing from base to so this is my emitter. If you look very carefully, this is my emitter, base, collector. I am only doing it the first time. I won't be doing it time and again as we move along, but just for your information's sake for the first time, base to emitter, the arrowhead is looking, which means the direction of the holes are in this direction, which means the electrons are moving from emitter to base, and therefore, this is basically an NPN transistor, right. Fine. This is an NPN transistor which you see NPN transistor which is there with me, and input side is always on the base side. So, you see most practically in almost 60-70% of the cases or 80% of the cases, you give the signal or give the input to the base side only, right, and try to take the output either from the collector or from the emitter. In this case, we are taking from the collector, and let us see how it works out. We will see one by one as we move along. Let us do one thing therefore, that let me keep my V in to be, so let us look at the digital part of it. So, if my V in is 0 or my V in is 1, 1 means let us suppose say VCC or large value, and 0 means 0 voltage, right. This is the condition which I am maintaining. Now, when my V in equals to 0, right, then my base emitter junction is cut off, right, and therefore, it is no current is flowing, no IE is flowing, and therefore, no current will be flowing through the circuitry, and my V out will be therefore equals to VCC at when, at V in equals to 0. So, when my V in equals to 0, my V out equals to VCC. Now, let me take V in equals to very high value, let me say, let me make it switch it on, which makes that this transistor is on. This transistor, when it becomes on, this potential will go to ground, and therefore, when my V in equals to VCC, my V out equals to 0, and therefore, this is how inverter BJT inverter is designed, right. Very simple, straightforward, from very first principles of circuit theory, you can predict the value of output voltage with respect to the input voltage which you see, and very straightforward way of looking at it. Also, you can, if you want the mathematical derivation, I can write V out to be equals to VCC minus IC into RC. IC is the current flowing through this domain, IC into RC. Now, if IC equals to 0, right, I get V out equals to VCC, and if your IC is very large quantity, then this will be very as close to VCC, and therefore, my V out will be equals to 0, right. And therefore, I can safely say that depending on the value of collector current, my structure, my device, which is NPN or transistor, can be switched on or off. So, basic switch, right, nothing very extraordinary difficult, is simply a basic switch which will switch from on state to off state and vice versa. I just shown it here in this diagram. In the next class, what we have learned therefore is a common BJT in a forward and reverse modes. We have also looked into the concept of base width modulation effect, and we also looked into BJT as an inverter. We will go into details if required at the later stages, and in the next lecture, we will be looking into BJT common emitter configuration working principles, right. With that we finish this lecture. Thank you very much.